In this video, we'll introduce you to artificial intelligence, or in short, AI. Meet Toby. And guess what? Toby is an AI. But what is AI? You probably recognize AI mostly from the movies like The Terminator, WALL-E, The Matrix, or others, right? For many of us, AI is the digital assistant we carry in our devices or an intelligent machine from a movie. There are many definitions of AI. AI for All, which is a nonprofit organization whose goal is to promote inclusive AI, defines AI as a branch of computer science that allows computers to make predictions and decisions to solve problems. For Kittle, AI is the ability for a computer program or machine to think and learn. From the academia side, John McCarthy, who coined the name artificial intelligence, defines AI as the science and engineering of making intelligent machines. According to Russell and Norvig, authors of the bestseller AI book Artificial Intelligence: A Modern Approach, AI is the study and design of intelligent agents, where an intelligent agent is a system that perceives its environment and takes actions that maximizes its chances of success. So, the ability to build intelligent agents is at the core of AI. According to Russell and Norvig, there are 4 schools of thought. The first school is about designing agents that think rationally. In other words, agents that use logical deductions to make decisions and inferences about the world. This school was widely adopted in the early days of AI to build intelligent agents that use logical reasoning to decide about its own actions. The second school of thought involves agents that act rationally, where intelligent agents do the right thing. A rational agent takes optimal actions and adapts to the world by optimizing some measure that maximizes its chances of success. For example, a self-driving car needs to find the optimal plan to go from point A to point B. Such a plan can take into account maximizing the comfort of the passenger, respecting the rules of the road, minimizing the time it takes to get to the destination, etc. Keep in mind that perfect rationality may be hard to achieve because the world is complex and there are many constraints. For example, deciding the best move to make in chess can be infeasible for an agent when time is limited. The third school is about agents that think humanly. It involves understanding the brain and how the human mind works. It is connected to cognitive science, which studies human intelligence and behavior, and neuroscience, which studies the nervous system. The last school of thought is about building agents that can act humanly. That is, to mimic human or animal behavior, even if the processes used are fundamentally different. A notable concept of this school is the Turing Test, which was proposed by Alan Turing in the 1950s to determine whether an agent is intelligent. Today, the predominant AI approach with tremendous progress is the one that builds agents that act rationally. We see much progress with agents that think humanly as well. Let's dive in and start with one of the most visionary AI researchers of all time, Alan Turing. Widely considered to be the father of artificial intelligence, Alan Turing was a British mathematician best known for being a codebreaker during World War II. In his seminal paper Computing Machinery and Intelligence, he laid down major components of AI, including language, knowledge, learning, and understanding, as well as proposing an operational test for intelligent behavior called the Turing Test. The Turing Test is a general test to determine whether or not a computer is able to think like a human. A computer passes the test of intelligence if it can fool a human interrogator into believing its results were human-made. For example, which of these two digits was written by the AI? Most people guessed correctly that this was written by the AI. Therefore, the AI has not passed the Turing test. Let's take a second example. Listen to the audio samples above. Wow, those were some nice tunes. Now, can you guess which of these was written by the AI? Here are the AI's music samples. That was a little harder, wasn't it? Therefore, this AI has passed the Turing test. You might be wondering, why AI? Well, AI is a revolution. To put it in the words of Andrew Ng, notable AI researcher and professor, just as the Industrial Revolution freed up a lot of humanity from physical drudgery, I think AI has the potential to free up humanity from a lot of the mental drudgery. Then, since AI is a revolution and can be our intellectual extension, where can we use it? Well, AI can be used in a broad range of applications including computer vision, where we teach computers to understand the visual world around us. An example is self-driving cars and their ability to identify objects that they drive by, and their ability to possibly adjust their actions accordingly in response to visual input. Natural language processing is about teaching computers to meaningfully interpret human languages. For example, we have spam detection filters for emails and text messages to prevent scams. Thank goodness for that. Spoken language processing is where we teach computers the recognition and translation of spoken languages. Examples include digital voice assistants that come with most of today's smartphones. What's the weather today? Thank you. Robotics, where we design and teach machines to perform physical tasks that are traditionally performed by humans. For example, nowadays, manufacturing industries rely heavily on robots to perform repetitive or complex tasks. Planning, where we build algorithms and autonomous agents that can automate planning and scheduling in a strategic manner. An example could be calculating the fastest route between 2 points, a feature which exists within most map services today. Games, where we program intelligent agents to solve or play certain games, and come up with optimal gameplay strategies. For example, scientists have developed numerous bots for the board game of chess over the past few decades. Good luck beating these, by the way. As AIs, they are extremely strong players. AI has a compelling and rich history that can be divided into 4 eras. The gestation of AI happened between the 1940s and 50s. Then, between the 50s and 70s, AI has known a big early enthusiasm and great expectations. The era of the 60s to the 90s is known for its knowledge-based AI, and finally, from the 90s to today, AI became scientific. First, the gestation of AI. In the early 1940s, we started seeing the early signs of AI. The most prominent ones started with the seminal work by McCulloch and Pitts. They showed we can mimic the activity of a biological neuron with an artificial neuron. A biological neuron is a nerve cell representing the functional unit in the brain, which contains an average of 86 billion neurons connected to one another. Each neuron has the ability to receive and transmit nerve impulses. A neuron is composed of 3 parts: dendrites to receive impulses from other neurons, a cell body to process them, and an axon to transmit the information to other neurons. An artificial neuron is similar and mimics this functionality. It can take a set of binary inputs that the neuron body aggregates by adding them up. If the sum exceeds a threshold value that can be adjusted, then the neuron fires by generating an output of 1. If the sum does not exceed the threshold, then the neuron outputs a 0. The neuron can learn propositional logic expression, that is, an expression that combines statements with connectives such as and, or, etc. In 1950, Alan Turing published his paper Computing Machinery and Intelligence. Besides proposing the Turing Test, he laid the ground for major AI concepts including language, knowledge, learning, and understanding. He had clear vision for a full AI agenda. (1956) was marked by a seminal event in the history of AI. The summer research project on AI took place at Dartmouth College in Hanover, New Hampshire. The gathering was proposed by John McCarthy, joined by Marvin Minsky, Nathaniel Rochester, and Claude Shannon. The event gathered 20 participants to discuss ideas about the thinking machines. It is largely recognized as the event that kicked off the field of artificial intelligence. In 1956, Arthur Samuel, a pioneer in game theory, developed at IBM a checkers playing program using reinforcement learning, a way to teach the machine to self-learn. His program was able to outperform an average player, and was even shown to the public on TV playing against master player Robert Neely. Samuel's checkers marked an important milestone in AI and game theory, and constituted the precursor of today's famous AIs like IBM Deep Blue or DeepMind's AlphaGo. In 1958, McCarthy invented Lisp, a high-level programming language used in AI research that dominated the field for 30 years. He also wrote the article Programs with Common Sense that laid the ground to symbolic AI, knowledge representation, and reasoning. Between 1963 and early 1970, Minsky's students developed what is known as microworlds, to solve problems in algebra, integrals, and geometry. The most famous application of block worlds was Sherdloo, a natural understanding program developed by Terry Winogrand at MIT between 1968 and 1970. Sherdloo is an AI that can understand and discuss some subjects in English. It can manipulate toy objects and respond by taking actions or asking for clarification. The Sherdloo program was written in Lisp and integrates syntax, semantics, inference that makes it capable of logical reasoning, and deduction. The early 60s marked the development of the first neural network, which is a network of neurons. Bernie Widrow and his student invented Adeline. Meanwhile, Frank Rosenblatt invented the perceptron. Keep in mind they were both built upon McCulloch and Pitts neuron, but this time the inputs can be real valued rather than only binary. and there are weights associated with them to adjust their importance. Just like McCulloch and Pitt's neuron, the inputs are aggregated but this time with a weighted sum, and the neuron fires accordingly based on the neuron adjustable threshold. Between 1966 to 1972, Shaky the robot was invented by a team of AI researchers at Stanford. It is the world's first mobile intelligent robot that could sense the world and use logical reasoning to make decisions about its own actions. Shaky could sense, learn, use early navigational techniques to plan, carry out plans of action, and communicate in simple English. The robot was named Shaky because it shook a lot when it moved, as stated by one of its inventors, and hence its name. Its hardware was not very sophisticated, however, its AI system was quite advanced. It considered an important milestone in AI history as it gathered many AI capabilities, including sensing, planning, language, and execution in the same AI. It is recognized as the precursor of self-driving cars, today's robots, and even Mars rovers. Today's Shaky is in the Computer History Museum in California. Unfortunately, the interest in AI began to wane in the 60s, mainly because early AI systems were developed on toy examples and therefore did not scale to large and complex problems. For instance, the perceptron was deemed too simple and was limited to linear problems. Consequently, funding for AI research was reduced significantly. Then, an idea emerged. How about incorporating domain knowledge to encode information about the world? This idea led to the creation of what is known as expert systems that can simulate human decision-making processes using rules. Expert systems like Dendril in chemistry, or Mycin in medicine, and others were successfully developed and turned AI into an industry in the 80s. However, expert systems were limited because they were hard to build and maintain, as they could not handle uncertainty about the world nor learn from experience. Consequently, AI research slowed down to a period known as the AI winter. The failure of expert systems was an incentive to the development of a more successful, scientific, and unified approach to AI from the 1990s to the present. Many subfields came together to make AI a success. First, the community turned to connectionist approaches, that is, using neural networks instead of symbolic logic. Furthermore, many neurons can be put together in a network and learn using the backpropagation algorithm. Inputs are fed into the neural network and then errors are backpropagated to help fix the parameters. Neural networks are better suited to address the imperfections of the world. Also, the process goes on with feedforward and backpropagation as the network learns from input data and adapts its parameters to a variety of imperfect inputs. The failure of expert systems also led to the incorporation of probability, rather than Boolean logic. Why? While Boolean logic is rigorous and powerful to model certainty, we are left with a large number of problems that require modeling uncertainty. The theory of probability provides a rigorous framework to reason about uncertainty, quantify it, and study the laws that govern chance. Probability allowed AI to make a huge leap by modeling uncertainty in applications as diverse as machine translation and robotics, to cite a few. Another important ingredient in the success of AI is using machine learning. That is, learning from experience, from data, rather than hard coding that can be tedious and fragile. Developing machine learning was facilitated by the availability of benchmark datasets and data repositories that helped researchers in the design and testing of their algorithms. Examples include the MNIST dataset for digits or the ImageNet repository for images. This helped overcome the limits and availability of toy examples that AI was using earlier. Furthermore, collecting and using data for machine learning was facilitated by the World Wide Web that made big data available in different forms, like text, images, audio, video, genomic, and social networks data. With big data and machine learning and AI success in vision, games, machine translation, and speech recognition, AI finally regained its lost commercial and public interest. The success was empowered by events like the participation of the IBM Watson AI and the TV quiz show Jeopardy! Watson demonstrated advanced AI capabilities including speech recognition, search, natural language processing, information extraction, building answers, converting them from text into speech, and interacting with the game. IBM Watson outplayed two human Jeopardy! Champions. This was a great moment and a boost for AI. The last but not least ingredient to AI success is deep learning. That is, using a type of neural network that is called deep because it is made of many layers of neurons. One example is the use of convolutional neural networks. While they were invented in the 1970s, it was only starting 2011 that they could be used at their full capacity. This is thanks to the use of powerful hardware like FPGA, GPUs, and TPUs that can provide the computational power needed to handle many layers with billions of parameters to find. This, along with machine learning advanced algorithms trained on big data, brought AI to the next level into what is now known as the AI Spring, where AI is a flourishing multidisciplinary field. Now that we've covered its history, let's talk about the future of AI. The future of AI needs to be governed by ethics. But what do we exactly mean by ethical AI? Interpretability is one component. Growing research on explainable AI aims to interpret complex and incomprehensible models that we call black box models because they are opaque. We can think of interpretability as opening the black box and understanding how it works. All models must be accountable and interpretable in order to ensure they are inclusive, increase our confidence in using these models, and gain knowledge and insight related to the task at hand. Bias is another important component in building ethical AIs. The data we use to build AI models can include human biased decisions. For example, a data set to be used for recognizing human faces might unfortunately have fewer faces of a certain skin color in proportion. As a result of this, phone cameras tend to have trouble recognizing darker-skinned faces. Fair AI aims to reduce bias such that decision-making is fair, ethical, and inclusive. Last, but certainly not least, AI education is a very important component. We should promote AI education to empower the younger generation with AI knowledge as they grow. This means allowing AI education to students regardless of nationality, race, class, or gender. As we advocate for an ethical future of AI, it makes sense to talk about a few prominent concerns AI scientists, lawmakers, and the public have. Stephen Hawking puts it best. Success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last unless we learn to avoid the risks. There is a lot to take into consideration as far as AI concerns go. Relevant questions include: how will AI impact our jobs, cities, and laws? Should we be afraid of AI? Is AI a threat to humankind? What do you think? Still, AI has a huge potential. To put it in the words of Jan LeCun, co-recipient of the 2018 prestigious ACM-AM Turing Award, our intelligence is what makes us human, and AI is an extension of that quality. Indeed, with AI, the future has the potential to be clean. Think about cleaning robots, self-driving cars using electricity, reduced traffic and pollution, clean renewable energy, and smart cities. With AI, the future has the potential to be fair. Think about how AI can be used to identify and eradicate injustice and bias and promote fairness in accessing education, healthcare, employment, and services. With AI, the future has the potential to be healthy. Think about personalized medicine, to fitness, to AI assisting physicians to make accurate diagnoses, to deciding about effective treatment options, to cite just a few of the potentials AI has to advance medicine and science. AI can help us reach these goals and many more, for humanity to be happy. Thanks, guys. There's more to come, so see you soon.